Hi there. So I wanted to give you some hints on rotation part 2. I know number 1 is not assigned, but I thought there might be some things in number 1 that might help. So if we take a look at number 1, what you know is the torques must be balanced, right? R cross F, which is mg, must equal R cross F, which is mg. If we come to the angular acceleration, again, you have to keep in mind that you need to use Newton's second law for translation, sum of F equals ma, and Newton's second law for rotation, R cross F equals Ialpha. So since the acceleration is the same for both blocks, has to be, or they would jump off the pulley, I can say I'll just pick M1, but I can sum all the forces on M1 and get Newton's second law for translation. And for me, I think I told you this previously, what I like to do is find tension with Newton's second law for translation and then plug that tension in to R cross F, where the F is tension, equals I alpha. And anytime, I guess here, you're just solving for alpha, but frequently they want the linear acceleration, which means you would substitute in for alpha in this equation a over r, linear acceleration over r. So moving forward, if you find the angular acceleration here, they want the tension. That's pretty straightforward. The linear speed is just a kinematics equation. I would personally choose v squared equals 2ax. Okay, so this one is yours, number 2, and let's see, surely you can find the torque. Remember, torque is R cross F, and torque is I alpha, where I is rotational inertia. I would remind you that just like A is change in linear velocity over time, so linear acceleration is change in linear velocity over time. Angular acceleration is change in omega over time. If we come to power, remember that power is a change in energy over time, right? So a wheel has a rotational inertia, blah, blah, uniformly accelerated. So look at the change in rotational energy, right? 1/2 I omega squared. So how does that change over time? And that should work it out for you. Let's see. Number 3. Angular acceleration alpha, again, change in omega over time. Angular momentum, when I think of the things angular momentum can equal, I just sort of rest on linear momentum, right? So linear momentum P equals mv, so angular momentum L equals I omega, so that's one way to go. And the other thing is that that angular momentum L equals R cross linear momentum, or RMV, if R and V are perpendicular to each other. I think you can find kinetic energy. So 4 looks like a center of mass problem. Let's see, is it center of mass? Kinetic energy? No, maybe it's not. Kinetic energy. Okay, so you're given n, you're given the length, you're given omega, right? And you're asked for kinetic energy. I think you're going to need 1/2 I omega squared, but you are going to have to get the rotational inertia. That's the deal here. So the system's rotational inertia is mr squared for each mass, and you'll have to figure out what those r's are, I believe. Okay. 5, anytime I see something like this, it's rotational energy. So if something's rolling, it has linear translational kinetic energy, 1/2 mv squared. And as it goes up, I can see that it, but if it's rolling and translating, okay, so translating, like a box, if a box could slide from left to right, and that would just be translating. A bowling ball could roll down the hall, and now that bowling ball is both translating, because it's moving from left to right, and rotating, right? So if I have 100 joules of energy, in the first example, all 100 joules of energy can move the box, can translate the box. So the box can have a kinetic energy, translational, 1/2 mv squared of 100 joules. But if I roll a bowling ball, the translational kinetic energy, 1/2 mv squared, can only be part of the 100 joules, because I have to use some of that 100 joules to rotate it. So it's like I ate my Wheaties for breakfast, and I can walk down the street and use that Wheaties energy to walk down the street, or I can walk down the street singing at the top of my lungs and clapping my hands. And if I do the second thing, then I can't walk as far on those same Wheaties. So let's see. 6 is yours. It's a non-uniform sphere. Let's see. Non-uniform sphere, rotational inertia I. The incline is frictionless. So, I mean, if there's no friction, it takes friction to torque something, to make it roll. So if you look up here, the radius of the ball and friction, you would, if there were friction, it would tip the ball over and cause it to roll. If there's no friction, the ball is just going to slide down just as if it were a box. Okay, so you don't have to consider rolling at all here. But when it's rough enough so the ball doesn't slip, now you have to consider that it's translating and rotating. This is that same problem again. This is just kinematics right here. I would use v squared equals 2ax. I know you're not solving this one, but just trying to give you some hints for some other things. If we go to number 8. Oh, sorry about that. There we go. Okay, so number 8, again, it's conservation of energy. You just have to look at the fact that the wheel is rolling and translating, so that's important. The middle one is kinematics. I would probably use that same thing. Watch out, though, the height. Note that let's see, what's the height and rest. If I called the hypotenuse of the ramp x, yeah, just note that h over x, that sine theta would equal h over x, okay? So I think that's going to help you at some point, but I'm sorry, h over x, yeah? So you got to be careful and think about, is what I need, how much it, if I'm reducing gravitational potential energy, then I'm looking at h changing. If I'm looking at how far it actually moves, like as displacement or distance traveled, then I'm looking at the hypotenuse. So just be careful of that. What is the minimum coefficient of static friction necessary to prevent the wheel from slipping? So when the wheel doesn't slip, if I sum all the forces on the wheel, they are, let's see, I'm going to put the wheel right there. They are the parallel, well, I mean, I can just look at it right here, the parallel component of mg, right? That's a force on it, minus the frictional force acting the other way. And if those two along the plane balance and there is no acceleration for the wheel with respect to the plane, then it is not slipping. Think about it. If the wheel accelerates with respect to the plane, then it's slipping. So if I say for this, sum of F equals MA on the wheel, and let's see, let's pause this. Okay, I think I can show you a couple things now. So if I say, FG is there, and the components are parallel and perpendicular, and there's normal, yeah. Then, so let's see, there's a mg, what, there's theta, sine theta, acting down the plane, and friction acting up the plane. So if I say sum of F equals MA and there's no acceleration, then mg sine theta would equal force friction. And what that would mean is that the wheel doesn't accelerate with respect to the plane. So there's that. So moving on, if I looked at 9, sphere partially hollow, what's the minimum coefficient of friction? On this one, for the ball to roll without slipping when released from rest on the incline. Okay, if we take a look at 9, 9 is exactly the same as 8, except that, let's see, there are some different variables. There are a few things different in the notation. The rotational inertia is a little different. So I'd like to work 9 with you. If we move on to 10, if the incline is frictionless, the block slides on a frictionless surface, it slides up. Oh, okay. So this problem is like throwing an apple up in the air. It's slow, 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 slow. Right? So the apple would, if I do a motion map, it would be like this. Slowing, 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 stop. Speeding up, speeding up, speeding up. I don't know why my apple gets smaller when it goes up and bigger, but on the way up it slows to a stop, and on the way back it speeds up. And if there were no air resistance, it would speed back up to the same thing. So in this case, it's just on the side, right? It slows to a stop and then it comes back down. If it comes to a rest, hopefully you can see that this is a conservation of energy problem. Part A is. And it looks to me like Part B is too. So on Part B, what you need to do is you need to consider that the energy is all 1/2 mv squared when you start, and when you end, right here, you have both the gravitational Ug, but you also have the work done by friction, right? So you have to consider what that is. So F dot X. All right. So let's see. I wonder if I can do this without drawing. No, I don't think I can. So if I move on past 10, oh, this is also 10. Let's see if you need help with this. Conservation of energy again. Watch out, translating and rotating. For C, Part D, with no friction, things act like a box. Okay, we're going to skip 11. We're going to do this as a sort of as a lab in class. Let's go on to 12, one of my favorites because I love birds. So let's see. When I see something like this that's on a spinning thing, let's see, 2 spheres, light rod. They're telling you don't have to consider the rod in the rotational inertia. Small bird.